to start talking about polygons, okay? Now, polygons is just a multi-sided figure, okay? Many-sided figure. What I've done, this is a voiceover on the PowerPoint slide, so I make the PowerPoint slide available to you as well. Closed figure at least 3 sides and three segments. The sides intersect only at their endpoints, and no adjacent sides are collinear. So we'll see what that means. This is a polygon. This is not a polygon. Basically, this is not a polygon because of this second statement that no adjacent sides are collinear. So in this case, we've called this point, let's say Z, BZ, and ZC are collinear. So that violates this from being a polygon, and 2 adjacent sides intersect. So that's not a polygon. Okay, this is a polygon. Okay, we have what we call concave and convex polygons. So here's the example of the concave, and it kind of caves in on itself. The test for concavity is to say if I can take any 2 interior points and join them with a segment, and if that segment, any portion of it, is outside of the polygon, it then becomes a concave. Here, any 2 points inside the polygon, when connected with a segment, that segment will lie inside the polygon, so that's a convex polygon. So we have polygons, non-polygons, concave polygons, and convex polygons. Okay? We know we can classify them by their sides. Okay? Triangle is a polygon, is a 3-sided polygon. Okay? Quadrilateral is a 4-sided. Of course, there's many different kinds of quadrilaterals, squares, rhombuses, okay, parallelograms, rectangles. But in general, they are all 4 sides, and therefore they are quadrilaterals. Pentagons, okay, 5 sides, 5 angles. Hexagons, 6 sides, 6 angles. And of course, all the figures we're showing here are convex polygons, and that's usually what we end up talking about more often than not, okay? But whether they're convex or concave, they can still be classified according to these number of sides, okay? Octagon, 8 sides, like your stop sign, okay? Nonagon, 9 sides. Now, some of these are going to be unfamiliar names to you. Decagon, 10 sides. Dodecagon, 12 sides. And there's a concave dodecagon, as you can see. 12-sided polygon is a dodecagon. In general, we just call them n-gons, where n is the number of sides, okay? So 15-gon is a 15-sided polygon, a 34-gon is a 34-sided polygon, so on and so forth, because obviously we couldn't lose track of all these names. You know, we have the obvious ones that we probably all know from long ago, as we saw here, you know, the pentagon, hexagon, and octagon, but and I would like you to know the decagon and dodecagon, but in general, 12-gon is a dodecagon, and 12-sided, n-gon, n sides, right? Okay. Here's our theorem, which is going to be demonstrated with some of the subsequent slideshows you're going to have. Okay, guys, so we're back, and so here we go, and like I said, we're going to address these with some other slideshows. So basically, if we want to find out, you know, what is the total angle measure for any polygon, what we're going to do is we're going to separate the polygons into triangles, okay? And that we're going to accomplish by, by drawing one of the diagonals from one of the vertices. So here we can see, okay, that when we draw a diagonal in the quadrilateral, it separates it into 2 triangles. So therefore, there's 2 triangles. There's 180 and another 180. It's 360 degrees, okay? So a triangle or a quadrilateral must have an angle sum of 360 degrees, okay? Now we take another figure here, which of course we can see has 1, 2, 3, 4, 5, 6 sides, so it's a hexagon. And the diagonals from one vertex are separating it into 1, 2, 3, 4 triangles, okay? So now, So each triangle contributes 180 degrees. So we must have 4 times 180, or 720 degrees locked up in this hexagon, okay? So we're going to say there's a formula, and the formula is going to be given by this noted up here, where n is the number of sides, okay? So the number of triangles is going to be actually 2 less than the number of sides. Here, when we had a quadrilateral, we have 4 sides with 2 triangles. Here, when we have a hexagon, we have 6 sides, we got 4 triangles. So it's a number sides less 2 is the number of triangles times the 180 for each triangle. So that's the total angle measure. And here we go, explaining all that again. And this you can watch in conjunction with the other with my other videos to review. Okay. That concept that the total angle measure is the number of sides less 2 times 180, okay? So here we're going to start talking about the construction of these figures, and I got separate videos, okay? And this is construction of regular hexagons or regular polygons, in which case all the angles and all the sides are congruent and all the sides are congruent, okay? So what we have to do is we have to figure out this angle. And how do we figure out that angle? Well, this is telling us we have to rotate it 120 degrees. Now, that angle, we knew if we went back to this previous page on the hexagons, we have 720 total degrees. We have 6 angles total, so 6 into 720. The total angle divided by the number of sides, or number of angles, which is the same, give us the individual angle. So here, when we have wanting to construct a hexagon, we know the total angle is 720. So each of the angles A, B, C, D, all these angles down here are 120 degrees each. So what we're going to do, and we'll show you this on the other videos, is we're going to take each segment and rotate it through 120 degrees until we generate the figure, okay? And then when we generate the figure, we can generate all the diagonals. That's going to be another exercise we'll run through for you, okay? And we'll show you how to get all those diagonals. Of course, all you're doing is constructing those, as you can see, but there's we want to run through how we determine how many total diagonals are in the picture, okay? So, and that's the figure with all the diagonals is called the network, okay? Here's the dodecagon, which is 12 sides, okay? And of course, we have to figure out what is the angle measure here, okay? And again, we'll show you that, okay? And that angle measure is 150 degrees, okay? Because it's the total angle from the dodecagon divided by 12, which is the number of angles, okay? And we'll rotate that through, and we'll show you how that is constructed as well, okay? And then there's your rather interesting dodecagonal network, okay? When we're finished with that, we can generate this table, and like I said, this slideshow will be available to you as a slideshow, so you can keep these up and running and see how all these values are determined, okay? What we have are the number of diagonals from any one vertex, which is always 3 less than the number of sides. That's why we have this n minus 3. We have the number of triangles from each vertex, which is 2 less than the number of sides. We have the total angle, which is the number of triangles times 180, okay? We have the exterior angles, which always add up to 360. We have another slideshow, or rather another video demonstrating that, okay? And then we have the exterior angle, which is actually going to be the supplement of that interior angle, okay? So as you can see, these figures, the interior and the exterior, are supplementary. Then we have the total number of diagonals, which we go by this formula. I'm not going to worry about that too much right now. We'll see that coming later. So my suggestion, go through all the rest of the videos, okay? Go through this as a slideshow. Print it out if you want, because you want to know how we get these values, okay? A lot of important stuff coming your way, okay? So go over, review all those videos, and we'll be in good shape, okay?